In our today's session, we are about to see the applications of closed-loop configuration of op-amp. So as we know, op-amp is a linear device. The input of the op-amp can either be provided to the inverting terminal of op-amp or to the non-inverting terminal of op-amp. So when the input is provided to inverting terminal of op-amp in closed-loop configuration, the gain obtained from the op-amp will be equal to V0 divided by Vin, which is equal to Rf minus Rf divided by Ri value. So since the input is provided to the negative terminal, the non-inverting terminal of op-amp will be grounded. Thereby, the output is obtained in the negative form. If the input is provided in the non-inverting terminal of op-amp, the gain provided by the op-amp will be 1 plus Rf divided by Rn, and the V0 will be a positive result based on the input. So those derivations we are about to see for the non-inverting op-amp, for the inverting op-amp, and for the voltage follower circuit. So first, when we consider the non-inverting configuration of op-amp, the op-amp should be provided with the input at the non-inverting terminal, the positive terminal of the op-amp. So this input is provided at the non-inverting terminal of your op-amp. To the inverting terminal, we provide the input resistance Ri and the feedback resistance Rf. The feedback is taken from the output terminal V0 of the op-amp, and this end of Ri should be grounded. This is the configuration of op-amp in non-inverting mode. So thereby, when we apply the KVL, the current equations on the inverting terminal and the non-inverting terminal, we know that the differential voltage between the inverting and non-inverting output inputs of the op-amp, Vd should be equal to 0. And this Vd is nothing but the voltage in the non-inverting terminal minus voltage at the inverting terminal. So if we consider this is node A, take this as node A. So here the node B. See that at node B the voltage is equal to Vin. Thereby Vp is equal to Vin. And when we consider node A, at this voltage, node A, when we apply the current equation, Va minus 0 volt divided by Ri. This is the current flowing through Ri from the Va node, and plus Va minus V0 divided by Rf should be equal to 0 when we write the current equation at node A. So now from this current equation, we shall find what is your Va value is equal to. So Va value is equal to, taking in common Ri and Rf value, 1 by Ri plus 1 by Rf is equal to, taking this V0 to the other side. So it becomes V0 divided by Rf. So this Va is nothing but taking LCM, Ri into Rf, Ri plus Rf value is equal to V0 divided by Rf. So now cancelling the denominator terms of Rf, we get Va is equal to Ri divided by Ri plus Rf value into V0. Now since Vt is equal to 0, Va minus Vt, we know that Vt is equal to Vb minus Va value. Now considering this as 0, Vb is equal to Va is our expression. This gives us Vb is equal to Va. Now equating these two Vb values and Va values, we obtain the expression as Vin is equal to Ri divided by Ri plus Rf into V0. Thereby cross multiplying the terms, V0 is equal to Ri plus Rf divided by Ri into Vin. Now dividing these values, we get that 1 plus Rf divided by Ri into Vin is our V0. Thereby, the output equation of a non-inverting op-amp in closed-loop configuration is V0 is equal to 1 plus Rf by Ri into Vn, and thereby the gain value will be equal to V0 by Vn, which is 1 plus RF divided by RI. Now this is our gain obtained from non-inverting terminal of op-amp for closed loop configuration. Same manner, we shall find what is the output equation of inverting terminal of op-amp. So when we consider inverting mode of op-amp operation, the input should be provided at the inverting terminal, non-inverting terminal should be grounded. So when we consider the input at the inverting terminal, to the end of Ri, we provide our Vin. And Rf is the feedback resistance from V0 to I. Now when we write similar equation for current equations for this inverting inputs, this is our Vp which is grounded. Thereby Vp is equal to 0. And writing current equation as A, we get this equation as Va minus Vin. The other end of Ri has Vin. Thereby Vi minus Vin divided by Ri plus Va minus V0 divided by Rf is equal to 0. Now taking your Va value common out of this one, we get your Va is equal to Va into 1 plus Ri plus 1 plus Rf equal to V0 divided by Rf. So this is as usual and like the previous case. So we get here as Ri plus Rf divided by Ri into Rf, and this side is V0 divided by Rf. Cancelling out Rf terms, we get Va is equal to Ri divided by Ri plus Rf into V0. Now here, when we equate Va and Vb terms, Va is equal to Vb is equal to 0. Thereby, Va is also equal to 0. So when this is equal to 0, we get your expression for V0 in terms of minus Rf divided by Ri into Vin. Now this is our output obtained from inverting configuration of op-amp. Thereby the gain value is equal to minus Rf divided by Ri for the inverting configuration of op-amp. So these two are the basic configurations of a op-amp. Configuration of op-amp is the voltage follower circuit. So when we consider the voltage follower operation, the op-amp gain should be equal to 1. In such a case, the non-inverting terminal of op-amp is grounded and the inverting terminal without input resistance is connected to the feedback. Now this circuit is the voltage follower circuit of the op-amp. Now when we consider this Ri, the Ri value for voltage follower is infinity, and the Rf, the feedback value, the feedback resistance of the op-amp is equal to 0. So that's why this is a short circuit. Now when we consider the op-amp circuit, there will be whatever signal which we